Hello, good people. This is Calculus Early Transcendentals, and we are discussing applications of integration. And this topic on hydrostatic pressure and force comes from section 8.3 of chapter 8 in James Stewart's Early Transcendentals book. Okay, so we are going to go over how to set up an integral that represents the force against the side of a vertical plate that is submerged in a liquid that has a particular density. And we want to just point out some of the facts that should be given in the problem, and that is densities of fluids are usually measured in either kilograms per cubic meter or pounds per cubic foot. So we're dealing with the metric system and the U.S. customary system of measures. Good. So we know that experimentally it's been verified that at any point in a liquid, the pressure is the same in all directions. If you're any point in a liquid at a particular depth, so at a certain depth under the surface, anywhere at that particular level, the pressure is the same in all directions. And we also know that the deeper we go under a liquid, the more pressure it has. So pressure increases the deeper you go, and you can think of the if the density of a liquid is measured in kilograms per cubic meter or pounds per cubic foot, we can take a look at just a plate that is submerged at a particular depth under the surface of the water, and we can look at what is the volume, because remember cubic feet and cubic meters, cubic meters is a measure of volume of your liquid. And that is, you can have how many kilograms are going to be on top of that plate at that particular depth. So you can see where pressure would be increasing the deeper you go, because the volume would be much higher. You'd have a lot more pounds of on top of that plate if we were in the U.S. customary system. And we know that with uniform blocks of three-dimensional slice, that our volume is equal to the area of that base times its depth, right? So we just go ahead and put forth that if we want to find the mass of our water that's sitting on top of that plate, we would take the density rho and multiply by that volume, because we would get kilograms per meters cubed times meters cubed. That would be my volume. We'd be able to cancel our meters cubed and get to kilograms, so we can see what the mass is. And then we know from physics that force is equal to mass times acceleration, and we usually use g here equal to 9.8 meters per second squared, because that is the acceleration due to gravity. So in order to get to force units, which are in newtons, we would want to multiply by 9.8. So we just take that formula, the force equal to mass times acceleration, and we form the force here is going to be that density times that g times that area times depth, which was that volume. And we're just going to define the pressure on that plate to be force per unit area. And so we would just take that, divide on both sides of that force thing by A, and we would get that in U.S. customary units, not in U.S. customary, in the metric system, pressure is going to be density times g, which is that 9.8 times the depth of where that object is. Good? All right. And if we were in U.S. customary units, we know that the unit of force is pounds already, because it already takes into account the acceleration constant. And so if we had a fluid density of delta, so in the U.S. units, and this is going to be in the metric units up here, but in the U.S. units, our pressure is just going to be the density times the depth. And so that's why we use a different Greek letter when we're dealing with U.S. customary. All right, so the general process that we are going to take in order to set up the force against the side of a vertical plate submerged in water is we're going to first draw a picture label it with the facts that we have from our problem. How far below the surface of the liquid is the plate? What is the density of the fluid? What are the units of measurement? Is it in US or is it in the metric system? We're also going to want to place a vertical axis to identify where the position of 0 is on that axis. And you'll also want to name that axis X or Y. So the placement of that 0 is going to be very important because it will determine the expressions that we have for depth, and it will determine also determine the range of the slices, right? Because when we set up an integral, our limits of integration are always going to be the range of the slices that we have. And why do we need to use calculus on this? Because pressure varies. The deeper we go, the higher the pressure is, and pressure and force is based on pressure. So we also are going to be taking area. So remember back up at the top here that our force, if we just take this over here, if we define our pressure, we know that we can kind of identify the process that we're going to make, that we can say that force is going to equal pressure times area, right? So we will be building the area of a slice. We will be building the pressure on that slice, and then we will be putting those two expressions together and multiplying them together and to get our force on the slice. And then we will be adding our slices up. And since our pressure varies, we need to use calculus or set up an integral. All right, so back to this. So we do want to place a vertical axis and identify where the 0 is on that axis. We then want to draw an arbitrary horizontal slice of the plate that is submerged in the liquid. Sometimes you'll have a plate that's partially submerged, and that's fine, but we just want to draw a slice that's under the liquid. And that should be a horizontal slice that actually cuts that vertical axis that you have. So the next step would be, what is the area of that slice? And we're always going to be approximating the area with a rectangle. So we know that area is length times width, and the width of that slice is always going to be delta x or delta y, and it is all dependent upon what you named that vertical axis. Right? It will be a delta x slice if you named that vertical axis x, and it will be a delta y slice if you named that vertical axis y. Okay. The next step is that you're just going to find the pressure on that slice, and the pressure is either going to be that density that you're given times 9.8 times the depth, or it's going to be the density of the liquid times the depth if it's in US units. The expression that we have for depth is going to depend upon where you put the 0 on that vertical slice. If you put the 0 at the top of the surface of the liquid, then depending upon what you named your vertical slice, if you put the 0 at the top of your surface of the liquid, then the depth to your slice is going to be x if you named the axis x. It's going to be y if you name the axis y. But the depth of the slice is how far under the surface of the liquid that slice is. So you want to measure the depth d from the surface of the liquid. All right, so once you find your area of your slice and you find the pressure on your slice, then you want to put together the force on your slice, and that's going to be just the delta pressure times the delta area, and then you're ready to set up your integral. So the total force is going to be the integral of the force on all those slices, and the limits of integration are going to be the range of the slices that are under the surface of the liquid, and the limits of integration will definitely depend on where you put the 0 on your slice. All right, so I'm going to start with some simple ones to start and show you that process. All right, so here, let's just assume that we've got a rectangular plate that's submerged under water, and let's just assume here, since we've got feet, you can verify that usually in problems that you're given, they provide the density of your liquid. But you can always assume that it's water, and water has a density in US of 62.4 or 62.5. I'm just going to use 62.5. pounds per cubic feet. Okay, that's the density of your water. And we see here in the shaded blue, this is going to be the surface of our liquid, right? That's going to be the surface of the water. And we're going to be trying to find the force against the side of that rectangle. And it is 3 feet below. Okay, so there's my picture. It's drawn. I know how far below the surface of the water it is. The next step that I'm going to take is that I'm going to draw my vertical axis. And since it looks like the slices are going to be uniform, I'm going to put my 0 at the top. Okay, and I'm going to call my axis X. Next step, I'm going to draw a slice, and I'm going to just draw an arbitrary slice underneath, and it's going to be a horizontal slice. Since I named it X, the x-axis, I'm going to have a delta X slice. Good. I also know that the depth of my slice, since this is 0, the distance to my slice, my depth D, is just going to equal X, because a 0, if you start from position 0 out an arbitrary distance along an axis, it's just X. All right, so I already have that expression for D, which is nice. So what's my next step? I'm going to calculate the delta area, and I usually call that delta A, and that's going to be length times width, where my width is delta X, and my length of my slice is L, and I see here that it's always, for all of my slices, it's always going to be 2. So my delta area here is going to be 2 times delta X. Next, I have to build my delta pressure, and my delta pressure I call delta P, and since we are in US units, it's just going to be the density delta times the depth, and so that's going to be 62.5 times X, right? Because we determined that the depth of my slice from the 0 is just X. Now I'm going to build my delta force, and my delta force is just my delta P times my delta A, and my delta P is 62.5 X, and my delta A is 2 times delta X. Good. So we just have that this is 62.5 times 2 times X delta X. Now, based on where I put my 0, and I'm 3 feet below, what are the limits of integration that I have? I see that my slices start at 3, and they go 8 more units down, so it's going to go to 11. So that's going to be the range of my slices. So then when I put my force together, my total force is going to be the integral of my delta force, and the range of values that I have go from 3 to 11, and I'm going to get that this is equal to 62.5 times 2 times the integral from 3 to 11 of x dx, and that should be something that is easy to calculate. Good? All right. Just in the interest of time, I could say go ahead, integrate that. Next up, we've got another plate that is submerged in water, and water again has density of 62.5 pounds per cubic foot. Okay, I'm next going to calculate, and since we have a triangle, I can go ahead and do one step ahead, and I can put my slice in there. And if I put my slice in there, notice that not all of my slices are uniform like it was in the previous example. So I might have to use some similar triangles, because I'm going to have a delta X slice here, but I'm going to need to find my length, and my length is going to depend upon where I place my 0. Okay, so the expression for it. So I tend to, in this instance, I'm going to put the 0 at the top of the triangle, and so that's where I'm going to put it. I'm going to put 0 here, and I'm going to go down, and I'm going to label that X, and so I know that from 0 to the slice is going to be X, right? This distance is going to be x, because any distance out along an axis starting from 0 is going to be that arbitrary value named for the axis that you're going along. But this is the surface of the water, right? And so where does the 2 come into play? I know that then my depth here, which goes to the slice, is going to be 2 plus x, right? So I automatically know that the depth is going to be x plus 2. Okay, and that's where that comes. Also, since I put my 0 here at the top of my triangle, the range of my slices is going to go from 0 down to 5, right? That's going to be where my integral is. So now I need to figure out how do I build the area of my slice? How do I find that L? I'm going to go to some similar triangles here, and we know from plane geometry that if I've got parallel lines, right, which I do, and this is x, and this whole distance here is 5, and this distance here is 10, I have, and this is L here, I have 2 separate triangles here, and one triangle is a little triangle, and that little triangle has X and L, and I know it's going to be similar to the bigger triangle, and that bigger triangle is has distance 5 on the vertical and 10 on the horizontal, and we know that similar triangles have the same shape, but they're just different sizes, and their corresponding sides are proportional. So I can say here that L over X is going to be equal to 10 over 5, and I can solve for L here and see that that is equal to 2x. Good. So sometimes you have to, depending upon where you put your 0, you might have to incorporate some things from geometry or graphs functions to figure out what the length is. So what's my next step? I'm going to calculate my delta area of my slice, right? So slice, right? And that area is length times width. And my length now we have is 2x, and our width is delta x. What's my pressure? My delta pressure is going to equal, oops, it's a little messy there. My delta pressure is delta P, and that is going to be, since we're in US customary units, it's just going to be the density of my liquid and then times my depth, and the depth we determined was going to be x plus 2, right? Delta pressure is density times the depth, and we have that. Next up, our delta force is going to be the delta pressure times the delta area, and we're going to get 62.5 times x plus 2 times 2x delta x. And putting that together, we end up with 2 times 62.5, and I would distribute the x, and so we would have x squared plus 2x delta x, because I'm about to integrate. So my total force is going to be the integral of my delta force, and the range of my slices is going to be from 0 to 5, as we mentioned earlier. So this is just going to be 0 to 5 of 2 times 62.5 times x squared plus 2x dx. And that should be relatively simple to integrate as well. All right, so that's an example of where I didn't put the 0 at the surface, and you can see where the depth changed. Now I'm going to give you one that involves a circle. That's why I drew the picture already a little bit. Here it says, find the hydrostatic force on one end of a cylindrical drum with radius 3 meters if the drum is submerged in 10 meters in water that's 10 meters deep. So here we've got a metric system, and the density of water is 1,000 kilograms per meters cubed. Okay, so we want to use that. And in this case, we have a circle. So here whenever you have a circle, and we know if I just go forward and take a 2 steps ahead and I want to draw an arbitrary slice, you can see that the arbitrary slice is going to be different for each level. I mean, you'll have 2 that are identical because of symmetry, but in this case, I'm going to want to find that length, and it's going to be different, and I'm going to need to figure out. Well, the easiest way to work with circles is to place the center of the circle at the 0, or place the 0 at the center of the circle. So that's what I'm going to do here. I'm going to draw my axes because that's what my next step should be, and I'm going to put the 0 in the middle, okay, in the center. So that's where I put my 0. And the reason being is, and here we know that our radius is equal to 3, right? So if that's 3, if I put my 0 here, then I know that this is going to be 3 and this is going to be minus 3. And I know the range of my slices now are going to be minus 3 to 3. But on top of that, I also know that if I put my 0 there, then I know that this point, xy, is going to satisfy the equation x squared plus y squared equal to 3 squared. I also know that if I go out 0 out along the axis, if I go from 0 out, that's just going to be x. So this distance is going to be x. And I know by symmetry across that, this distance is going to be x. And so then I can see that my length here of my slice is going to be 2x, right? Where x is equal to the square root of 9 minus y squared, because it came from that equation. Good. I also know that if I labeled this the x-axis and I labeled this the y-axis, that I'm actually slicing the y-axis and I have a delta y slice. So now I can put together my expression for the area of my slice. So whenever you have a circle, put the 0 in the middle of the circle. Good. Now on top of that, let's see what the depth is so that we can put everything together pretty simply. So we do know that this is the surface of my liquid, and I'm on my way to saying what is the depth of my slice. Well, I do know from the fact of the problem that this total distance is 10 meters, right? And I know that from this 0, I do have, we've got, or from the very bottom of the circle, we've got 3 meters for the first radius, another 3 meters for the second radius, so that's 6. So I do know that this distance here is going to be 4 meters, right? Now, drawing my depth of my slice, this is the whole depth of my slice, right? That's going to be my D. Oh, let's see if I can do a straight line. That's going to be my D. And my depth is going to be 4 plus 3. And if I go from 0 down to my slice, we know from here to here is going to be y, right? You could call it negative y if you want to, so that you actually get the actual depth to that distance. I tend to just keep it at y to reinforce that any arbitrary distance out along an axis is going to be that variable. Because we do know in calculating the entire force against the side of the entire circle, we're really, if we keep that at regular y, we're really going to be calculating the force against this symmetrical slice, right? But we're doing the whole thing, so we should be good. But that depth is going to be 4 plus another 3 plus y. So we can say that our depth to the slice is going to be 7 plus y. Good? All right, so now I think we're ready to put together our delta area, delta pressure, and then our delta force. So here we go. So what is our delta area? That's going to be a length times a width. We figured out that it was 2x times delta y, but where x was equal to the square root of 9 minus y squared, we know that we need to have an expression in y if we have delta y, So we're going to replace that x with 9 minus y squared. And then we have delta y. That's our delta area. Our delta pressure is going to be, since we are in the metric system, it's got to be the density times the gravity constant times the depth. So this is going to be 1,000 times 9.8, and we figured out that this was 7 plus y. Good. And now we have our delta force is going to be our delta pressure times our delta area, and we can put that together, and we have 2 times 9,800, right, times 7 plus y times the square root of 9 minus y squared, delta y. And then finally, our total force is going to be the integral of our delta force, and the range of our slices goes from -3 to 3, because that's where our slices are according to that 0. So you see where you place your 0 determines the range of your slices, and you really only want to have the range also is determine how many of those slices are under the surface of the water. So we can put our 2 times 9,800 in the front, and we can go from -3 to 3 of 7 plus y times the square root of 9 minus y squared, delta y. I would distribute the square root of 9 minus y squared, and then I would split up the two terms into two separate integrals. One of them is relatively easy to calculate with the u substitution. That would be the second integral, and the first one I'd use a table entry. All right, so hopefully that was helpful, and